Hi guys, myself here Ramsu Sachari from C section. In this video, we will learn about virtual memory and the issues of implementation of virtual memory. Topics: Introduction, Issues of Implementation, Conclusion. Introduction: Virtual memory is a storage allocation scheme in which secondary memory can be addressed as though it were part of the main memory. The addresses of a program may use to reference memory and diagnosed from the addresses the memory system uses to identify physical storage sites and program generated addresses and translated automatically to the corresponding machine address. The size of virtual storage is limited by the addressing scheme of the computer system, and the amount of secondary memory is available not by the actual number of main storage locations. It is a technique that is implemented using both hardware and software. It maps memory addresses used by a program called virtual address into the physical address in computer memory. Implementation issues. These are the some of the implementation issues while we are implementing in virtual memory. Involvement with tagging, page fault handling, instruction backup, locking pages in memory, backing store, separation of poles and mechanism. Large physical memories. The amount of physical memory installed in a modern workstation is increasing rapidly. 60 years ago, a workstation was shipped between 4 MB of RAM and was expandable to approximately 32 MB. Today, a system ships with 32 of RAM and expand at least 128, and 512 is not uncommon. Large physical memories also increases the size of per page translation entries in the page table. The number of bits required to index all physical frames is 3 now, greater than 26. Also available is 32-bit PT entry. The next logic step is to use 64-bit PT enters per page, which doubles and storage overhead per physical page. In summary, the increase in physical memory size has revealed in current TLB coverage and increased the memory required to store translations. Space memory usage. The memory layout of a Unix process is well known. It consists of a program, text, and data at the bottom of the available user address space. The heap used for dynamic memory allocation sits above the text and data segment and is free to grow upwards during program execution. The stack lies at the top of the user address space and is free to grow downwards. This process memory layout efficiently divides the address space into the two contiguous regions which grows towards each other. The layout is efficiently supported by hierarchical page tables for two reasons. Contiguity means the page table is density populated and thus space efficient, and the TLB misses the page table itself can be minimized by revising TLB to the map areas of the page table corresponding to the known text, heap, and stack layout of a process. Memory mapped files. Memory operating systems provide memory mapped files which map portions of files into the virtual address space of a process. This allows I/O operations to be performed as simply memory access rather than the explicit simple calls. While this feature is convenient to the programmers, it increases the virtual memory usage and results in higher TLB miss rates due to the inaccurate TLB coverage. Memory mapped files are usually large and few in number and so have a relatively small impact on PT fragmentation. As well, the OS is free to map these files as it seems fit. These factors can reduce the impact of memory mapped files on PT and fragmentation. Single address space OS. Single address space OS. A single address space OS is mapping used for all processes, and so transaction table may have mappings for all the objects being referenced by the process on a host. This leads a drastic increase of the number of objects and future fragments of the page table. The compatibles are used at runtime to establish the mappings with the appropriate protection bits. As activity switches between process, it is necessary to quick change the protection between bits without affecting the translation. As well as there is no needs to be support for quickly changing and protection domain of a process for privileged operation and to support object-oriented programming models. The implementation of these features on current 64 architecture with software overload TBS is profitable because the TLB enters into the intended for individual address spaces and protection information. It is therefore necessary to modify the TLB refill holder, holder to combine information from a global transaction table with the appropriate process specification. Current strategies for solving the problems identified above can be divided into two groups. The first strategy involves changes the page table data structure to minimize TLB refill time and to cope with space address memories and new protection systems. The second involves to the TLB to minimize the number of misses. Page table structures. The page table structures is one of the approach to cope with large address spaces is to separate address translation from backing store management. The page table changes from one that maps all valid virtual address of the process to one that only needs to map pages residence in memory. This allows a structure designed fast TLB reloads to be used but requires a separate data structure for finding and backing store address and approaches to fast lookup is to use hashing to search a table of pages. Two basic techniques has been used: inverted page table and directly hashed page table. Inverted page tables. An IPT consists of two parts. The page table occupying the frame and associated protection information. A separate hash table is used to map page numbers to corresponding entries in the frame table. The advantages of IPT is to their size scales linearly with physical memory size. IPT is almost independent of virtual address space size and more importantly independent of the distribution of occupied virtual address space. This diagram shows the virtual address in inverted page table technique. Hash page table. This is another technique to overcome the problems of implementation. The hash table has been proposed to overcome some of the limitations. It is a more general variant and the hardware technique for TLB replacement in the Monots PC. The entire contains page number and frame number and protection information and are indexed using hashing. Collisions are resolved using methods such as chaining. The following diagram shows the virtual memory issues of implementation using hash page table. Conclusion. Traditional approaches to virtual memory address transaction are being severely taxed by the demands of modern operating systems. In particular, the move to be 64-bit architecture and desire to support single address space systems increase to size and the sparsity of virtual address spaces. While there is some work being among currently to improve TLB performance, these proposals do not consider the special needs of systems such as Mungi in translation and production functions need to be separated. Much work remains to be done to determine the best approach of implementing space address space systems on currently available processors which use software loaded TLB. Thank you.